Okay, so let's start today's discussion with ideals and quotient rings. Actually, we are just going to recall old things, but also at the same time keeping in mind that now for us, ring means a commutative ring with a multiplicative identity. We should not forget that. So let's start with the definition of an ideal. That definition is same as before. Let A be a ring an additive subgroup I. In the book, small German letters have been used to denote ideals. We cannot, however, write German letters here. It's a little difficult to write. So we will just use our ordinary Latin letters. Okay, so an additive subgroup I of A is an ideal of A if AI is a subset of I, where AI of course means the set of all elements of the form AB, where A belongs to A and B belongs to I. Okay, so you get the meaning of this definition. An ideal, of course, is an additive subgroup, first of all. And then this should be true. What does it mean? It means that if you take any element A from A and any element B from I, and you multiply that element B by A, then the product AB should again be in I. And here, this much is enough for I to be an ideal, because do not forget that we are in a commutative ring. Our rings are commutative. So if AB is in I, automatically BA is also in I. So that left-right business, you do not have to really worry about that here in this setup. The quotient group. So once you have an ideal of a ring, you know that you can form the quotient group of A by that ideal. We say quotient group because here we are considering A as an abelian group under addition. It is. And ideal by definition is a subgroup. Since we are in an abelian group, that subgroup is a normal subgroup. So we can of course consider this quotient group. And this quotient group inherits a unique multiplication which makes it a ring. See, we already know that we can define a multiplication of elements in this quotient group that will turn the system into a ring in Herstein's topics in algebra sense. However, now in order to call this a ring, it must additionally be commutative and it must have a unit element, or in our language in this book, a multiplicative identity element. Is it going to be commutative? Yes, because our original ring A is a commutative ring. So the quotient ring automatically will also be commutative. This also we know from Herstein. Will it have an identity element? Yes. Note that if one is the identity element in A, then the coset 1 plus I is the identity element in A slash I. We also know from group theory, we know that the elements in this quotient group are cosets. In fact, let's just write that now. The elements of this ring are the cosets of the ideal I in A. Actually, the term coset is for groups, for subgroups in a group. Here also, that's what cosets are. But additionally, we have more structure. A is not just a group, A is in fact a ring, but coset means just that. This is a coset of the subgroup I of the additive group A. And when we say in A, this means that the representative element of the coset A is coming from A. Okay, so these are the simple things we already saw in ring theory in Herstein. And what do we know about the relationship between this quotient ring and the original ring A? We know that this is a homomorphic image of A. But let's also write that this is called the quotient ring. We call A slash I the quotient ring or residue class ring. That's also another name. Of A by the ideal I. All right. Next comes the relationship between A and A slash I. The mapping, let's just call it phi. Usually that's how it's named. From A into A slash I. And what is the definition of phi? The image of A under phi is the coset A plus I. This mapping is a surjective. Surjective means onto. Ring homomorphism. We already know this result. In fact, in Herstein's algebra, this is lemma 341. Herstein. Okay, so you can go there and see this lemma. There we have this, but again, let's be careful. Okay, let's not be careless here. For us, ring homomorphism has a slightly different meaning than what it means in Herstein. In Hartstein, a ring homomorphism just has to respect addition and multiplication. But for us, it also has to respect the identity elements in the ring. Is it doing that? See, from this lemma, we know some things. We already know that this function respects addition, it respects multiplication, and at the same time it's surjective, that means onto. That we already know from this lemma in Hartstein. But does it also respect the identity elements? We have to see that. Okay. Note that. Otherwise, we can't call it a ring homomorphism in our sense in this book. So you just have to check whether phi maps the identity element of A onto the identity element of A slash I. Let's call the identity element of A 1. Then by the definition of phi, this is 1 plus I. But 1 plus I is the identity element of A slash I. So that is why it's okay to call it a ring homomorphism in our sense. It's a surjective ring homomorphism. And now next comes the correspondence theorem, which is also something we already know from Hartstein. And we are going to use this theorem left and right. Every time we link ideals of one ring to ideals of another ring, this theorem will appear in one way or another. So let's see the statement. So this is in fact, theorem means it's given as a proposition in this book. Proposition 1, 1. Now the proposition is written somewhat, the statement is somewhat compactly given. Everything detail is there, but let me just write it a little more elaborately, a little more formally. Let A be a ring and I be an ideal of A. Okay. Also, let what shall I write for these sets? I can call them anything. Let S be the set of all ideals of A that contain I. Contain I means S consists of, what are the elements in S? They are ideals of A, those ideals which contain I inside them as a subset. And T be the set of all ideals of A slash I. On T there is no further restriction. T is in fact the set of all ideals of this ring A slash I. Define a mapping psi from T to S. How are we defining this mapping? By this rule. So that means an input of psi is going to be coming from T. That means it will be an ideal of A slash I, some ideal. Let's call it J, you can call, or let me just call it J bar. Now, what is this? What's the rule? The rule is that it is the inverse image of J bar under phi. What is phi? Phi is that mapping which maps A into A slash I, and the rule that phi follows is this. So, is it making sense? Does this mapping at least make sense? When you take your J bar from T as an element of T, what is J bar? J bar is an ideal of A slash I. So basically, what is J bar? J bar is after all a subset of A slash I, a subset of this set. Okay, J bar is a subset of A slash I. So it makes sense to talk about the inverse image of J bar under phi. And what will that be? That will be a subset of A. Actually, it turns out that that is in fact not just a subset of A, but is an ideal of A, and that too an ideal which has I inside of it, which means that this is a legitimate element of S. And we have already proved in Herstein's topics in algebra that this psi is then a bijective mapping. It is both one-to-one as well as onto. So in that sense, it is a one-to-one correspondence between what? Between T and S, between the ideals of A slash I, which is, their collection is S, and the ideals of A which contain I, and their collection is T. Okay. So we have this result already for us, and because we are not stating here that psi is a ring homomorphism or anything like that, psi is simply a bijective mapping. So this result from Herstein simply just works here also. And in Herstein, this is your theorem 341. See, theorem 341, Herstein. So we have the proof there. We have in fact discussed it in detail there. So it's available to us for use, and we will use this every chance we get. Note that in particular, if T is finite, then S is finite and has the same number of elements as T has, and vice versa. Okay, so this means that if there are only finitely many ideals of A slash I, then an equal number of ideals of A exist which have I as I inside of them. Okay, so that is proposition 1.1. Next, we have this statement. If F from A to B is a ring homomorphism in our sense, then its kernel, we know what kernel is. It is the inverse image of 0. 0 means, of course, the 0 element of B. In other words, this is the set of all the elements of A which are mapped by F onto the 0 element of B. That is the definition of kernel, and we also know that this is an ideal of A, and just like that the image of the set A under F, which is going to be a subset of B, this is a subring of B. Now, we did not really pay too much attention to subrings in Herstein's algebra. So, although we have seen this fact that kernel is also an ideal, in fact, the notion of kernels of homomorphism gave rise to the idea of ideals in Herstein, if you recall. We first did what in Herstein? We introduced the notion of a ring homomorphism, and then we defined its kernel, and then we asked what properties will a kernel of a ring homomorphism have, and we proved some 2 or 3 properties. First, we proved that the kernel of a ring homomorphism needs to be a non-empty subset. It is a non-empty subset, and then slowly, gradually we uncovered these facts that, okay, not just a non-empty subset, it's actually a subgroup of the domain ring under addition. And then that other property also, that it engulfs multiplication from left side, from right side. And then only we got the idea that we can call this type of subsets of the ring something. And that's how the idea of ideals came. Okay, so it's already familiar to us that this is an ideal of A. But this we need to verify, okay. So let's just go through the verification sketchily. Sketchily means I won't really write sentences. Let us just show here only the details of how f of A is a subring of B. So you just take 2 elements A1 and A2 in A, so that you will get the 2 elements f of A1 and f of A2 in f of A. Now let us take their difference, because these then become 2 elements in f of A, and we are looking at their difference since f is a homomorphism. So this is f of A1 minus A2. So that is again the f image of some element in A. So this belongs to f of A. What does this tell us? This tells us that f of A is a subgroup of B under addition. Or to put it somewhat more compactly, is an additive subgroup of B. Okay. What else do we need for f of A to be a subring? It also needs to be closed under multiplication. To see how, we take the product of these 2 elements. Again, because f is a homomorphism, so respects multiplication, we get this. So this is again the f image of A1, A2, and A1, A2 is again an element of A. So this belongs to f of A. But that's not enough. We still have one more thing to show. We still have to show that f of A contains the identity element of the ring B. Do you remember that also we have to see. So this is where again the fact that f is a homomorphism comes into play. Because f is a homomorphism, and because A is a ring and hence by definition has an identity element 1. So f of 1 exists in f of A, but at the same time, because f is a homomorphism and so respects identity elements, this f of 1 is in fact nothing but the identity element in B. So the identity element in B is in f of A, and that's how this is a subring of B. Okay, so that's the verification. Oh, and okay, this actually, the fact that this kernel is A is an ideal of A. To see where you have this result in Herstein, you see lemma 332. Okay, there you have this stated as a fact in Herstein's topics in algebra. Besides these things, we also have this other fact. Also, so the mapping is from A to B, and this is the image and the kernel is this. Also, you have this fact. So this comes from your first isomorphism theorem of rings. And this is again theorem 3, this same thing also includes this. See theorem 341 Herstein. But we have to be careful again. Herstein doesn't fully show this. In Herstein's sense, it shows it fully. But in our sense, we still have one more thing to show. So let me go back briefly to the proof of this theorem from Herstein. If you remember, this is how things went in Herstein. Say you want to prove this from scratch. Say you do not have this theorem, but you want to prove this theorem itself in this special case. Then what will you do? What did we do there? We set up a mapping sign. Do not confuse this psi with that other psi we wrote. Okay, this is something else. And the definition of psi was this. So what will be our input? Our input is going to come from this quotient ring, which means that this input is going to be a coset of the ideal F inverse of 0 in A. So this is how it's going to look. And the definition of psi tells us that this is the F image of that A. This was the mapping that helped us prove that these two rings are isomorphic, and in fact this is the isomorphism. So in proving theorem 341, we went through the details of showing that this is an isomorphism, in fact an onto isomorphism, or if I want to really be absolutely rigorous about what I am saying, this mapping is a bijective ring homomorphism in Herstein's sense. So we already know from the proof of this theorem in Herstein that this function is one-to-one onto, it respects addition, it respects multiplication. But then what else? That it also respects the identity element. That's what we have to show extra. So to see that that is the case, you take the identity element of your domain ring, which is 1 plus the ideal F inverse of 0. By this definition, it will be equal to F of 1. However, F itself is a ring homomorphism in our sense, so F of 1 should be equal to the identity element in what? In B. In fact, here itself we have shown that. Okay. So that's why, besides having all those properties of being bijective, respecting the binary operations, this psi also respects the identity elements of these two rings. And that is why in Atiyah Macdonald's sense, this really is a ring homomorphism that is bijective. And so these two rings are isomorphic. Okay. It may be a little annoying to go back and forth between Herstein and Atiyah like this, but we have already done parts of this thing, so why repeat? That is why here we are only showing that much which we need to show extra. Also, there is one remark, purely notational remark, which is this. We will sometimes write x congruent to y modulo I to mean that x minus y belongs to I. You understand that in this context, I is an ideal and x and y are elements coming from that ring in which I is an ideal. Moreover, this notation is nothing new to us. In fact, in Herstein's topics in algebra itself, we saw this in group theory. When we proved Lagrange's theorem for finite groups, there we, if you remember, we introduced an equivalence relation. And the equivalence classes turned out to be precisely the cosets of a subgroup. And that equivalence relation had a subgroup here. And of course, elements here. Instead of having x minus y, there we had x y inverse belongs to the subgroup. Same thing here, because I is an additive subgroup of A, and in the additive subgroup, x minus y simply is just x y inverse. Okay, so this is just, instead of writing like this, sometimes we will write like this. Although there, when introducing this relation in Herstein, we talked about its origin, that is why this notation was chosen. But let's briefly see once more, okay. This of course comes from the familiar congruence modulo n from number theory. Say we have the ring of integers, and in it you know that you have the ideal consisting of all multiples of some fixed integer. Okay, so this is an ideal in Z. So according to this notation, when we say that, say you have two integers x and y, x is congruent to y modulo I if and only if x minus y belongs to I. But then what does that mean? That means that x minus y is equal to mn for some integer n. Now if the chosen n is non-zero, or in fact positive, then this will turn into the usual congruence from number theory, because then n would divide this, and that's what x being congruent to y modulo n means. So this is the source of this notation. Alright, so that much we had to say, or rather the authors had to say about ideals and quotient rings. Many more things are coming, but these are the preliminary things that we already know. Next comes zero-divisor. Zero-divisors, then nilpotent elements and units. And this is where a little confusion we will see. Okay, it is a little confusing. Confusing because the term zero-divisor means one thing for Herstein and a slightly different thing for Atiyah and Macdonald. Unfortunately, that's how it is. But it's not that they have some kind of beef and they just want to be annoying to each other. No, nothing like that. It's out of necessity. Alright, so let's start with zero-divisors. Let A be a ring. That means A is a commutative ring with identity element. It's understood. An element x in A is a zero-divisor, or is called a zero-divisor if it divides 0 in this sense. If x, y is equal to 0 for some y not equal to 0 in A. At first, this definition will look identical to the definition we have for zero-divisors in Herstein's topics in algebra. But there is a small difference. Let us see that difference. Now I will write Herstein. Okay. First of all, Herstein declares that zero-divisors are being defined only for commutative rings. This he had to say because Herstein also considers non-commutative rings. Let R be a commutative. If I do not write the full thing, you will get confused. an element x not equal to 0 in R is a zero-divisor if x y is equal to 0 for some y not equal to 0 in R. Did you spot the difference? The difference is in x. Atiyah and Macdonald's definition allows x to be 0. However, Herstein doesn't allow x to be 0. For Herstein, the 0 element is not included in the definition of zero-divisors. But for Atiyah Macdonald, 0 is included. But there is something more. You see, you just notice one thing. Suppose A is equal to 0. A is the 0 ring. Do you remember that we already have decided to not write like this by abuse of notation? We will just simply write 0, and we mentioned that from the context we will understand what this 0 is. So it is the 0 ring. That means in this ring there is only one element, the 0 element. So although Atiyah and Macdonald allow the 0 to be a zero-divisor, but in the 0 ring, 0 is not a zero-divisor. Why? Because for 0 to be a zero-divisor, you must have a non-zero element whose product with 0 should be equal to 0, but there is no non-zero element in the 0 ring. So in the 0 ring, Atiyah Macdonald's zero-divisor is not there. The only element is not a zero-divisor. Okay? Then 0 is not a zero-divisor. However, suppose that A is a non-zero ring. Okay? Non-zero ring means in Atiyah Macdonald's sense. Here, no matter what the ring A is, 0 will always be a zero-divisor. For, and the reason is this, for any y not equal to 0 in, or maybe this is a little confusing. I mean, this way of writing will be a little confusing. Let means let us choose some y in A which is not equal to 0. We can choose some such y because A is non-zero. Since 0y is equal to 0, from elementary properties of rings, this is always true, we know that. So 0 is a zero-divisor. So in the 0 ring, 0 is not a zero-divisor, but in any non-zero ring, 0 is always a zero-divisor. So if you are working with a non-zero ring, which is almost always the case, at least one zero-divisor is always there, which is 0. Besides that, you may have other zero-divisors as well, which are non-zero. And when it comes to non-zero zero-divisors, Atiyah and Macdonald's thing coincides with Herstein's thing. Okay. In this part of the definitions where we need a non-zero element y, that's the same. But the only difference is that Herstein doesn't include 0 in the collection of zero divisors, but they do. Okay, so that is the difference. And because these things are different, automatically integral domain will also be different in these two books. In Atiyah's book, this is what integral domain is. Let me write it in another paragraph. Let A not equal to 0 be a ring. An integral domain, according to Atiyah Macdonald, is by definition non-zero. The zero ring is not included in the list of integral domains, according to this book. If A has this part may be very confusing, okay, watch carefully. Non-zero, zero divisors. If A has no non-zero, zero divisors, then A is called an integral domain. Now, before going back to Herstein and seeing what he calls an integral domain, let us just digest this one a little bit. We have already understood that A needs to first of all be a non-zero ring. Then, see, automatically when A becomes a non-zero ring, we have a zero divisor which is 0. That is always there. But if that is the only zero divisor, if there is no non-zero zero divisors, then A is called an integral domain. In other words, a non-zero ring, this is how we can simplify this. A non-zero ring in which the only zero divisor is 0 is called an integral domain, according to Atiyah and Macdonald. However, what does Herstein say? Herstein's case is a little unfortunate. I don't know why he did it, but it is what it is. Let R be a commutative ring. R is called an integral domain if it has absolutely no zero divisors. Let us now see the differences. You see, R needs to be a commutative ring. Our ring, however, besides being commutative, also has a unit element, an identity element with respect to multiplication. That is not necessary for Herstein. It just needs to be a commutative ring, like the ring of even integers. This is a ring which is commutative but which has no identity element with respect to multiplication. And then, such a ring is called an integral domain if it has no zero divisors. Recall that 0 is never a zero divisor according to Herstein's definition. So this part of the definition coincides with this. But what does not match is that, unfortunately, this definition of Herstein includes the zero ring in the class of all integral domains. Why do I say that this is unfortunate? This is unfortunate because some results which are in general true for non-zero integral domains according to this definition fail to be true when the integral domain is zero. Oh, by the way, how is it an integral domain? Is it commutative? Yes. Is there a zero-divisor? No. Zero anyway is not included in Herstein's definition of zero-divisors. So by definition, this is an integral domain. Now, one such result which fails is this, that every finite integral domain is a field. This is a finite integral domain. Is it a field? No. And this is where Herstein makes a little mistake when he just simply, I should say carelessly, simply states every finite integral domain is a field. Ideally, according to his definition, he should have stated instead this: every non-zero finite integral domain is a field. But okay, we understand. So, these are the differences. So, in our non-zero rings, we have at least one zero-divisor, that is 0, but there may be others. Okay, so that's what we need to remember right now. Man, these things become so confusing. Oh, and let us also note this. Because we are comparing so much, let's note this also. Every Atiyah Macdonald integral domain is also a Herstein integral domain. But not conversely. If you have an integral domain in Atiyah's sense, Atiyah-Macdonald sense, then that is also automatically a Herstein integral domain. How? How is that true? Suppose that A is Atiyah-Macdonald integral domain. This means that A is, first of all, a non-zero ring. Fine. What do we need in Herstein? We need a commutative ring. Our rings already are commutative. Fine. What else do we need? We do not need any zero-divisor according to Herstein's sense. And Herstein's sense matches with Atiyah-Macdonald's sense for non-zero zero-divisors. That means we do not need any non-zero zero-divisors. Yes, that is true. The only zero-divisor according to Atiyah's sense in such a ring is 0, but which Herstein doesn't call a zero-divisor. So that's it. That's how we have this. How is the converse not true? The converse is not true in this somewhat silly way, because this is an integral domain, this zero ring, according to Herstein. But according to Atiyah and Macdonald, zero ring by definition is not an integral domain. Okay, so in that way. Now, examples of integral domains, of course, are the familiar examples with which we, in fact, started this entire discussion. In the beginning itself, we gave these two examples. One of them comes from number theory and the other one comes from algebraic geometry. So, this is an integral domain in our sense now. Is it a non-zero ring? Yes. Does it have any non-zero zero-divisors? No, it does not have. In fact, in our axiomatic construction of the integers, in Terence-Tau's analysis, there was one result where we proved from scratch that this has no zero-divisors. If you are interested, this was the result. See proposition 416. Actually 416 shows that this is a ring. Okay, that's what it shows. Because it's an analysis book, so the algebraic matters don't really have that much importance, but it's a nice thing that Tau at least mentioned the things, the terms from algebra. In remark 417, he mentioned this fact that collectively those properties that this system has, they are expressed by saying that it is a ring, a commutative ring. In fact, he mentions that also. And the fact that there are no zero-divisors, he shows in proposition 418. In Tau. And in the statement of this proposition, there is a line also, like a heading, that integers have no zero-divisors. So there also, in that analysis book also, this term zero-divisor has been mentioned. What about this? This kind of rings we have seen in the last section of Herstein's topics in algebra, where you have that, the name of the section I think is polynomial rings over commutative rings, that section. And there also, this is how I should write, C, and the result that tells us that this is an integral domain is lemma 311.1. In fact, see the corollary to okay, and where K is a field. The definition of fields, luckily, is there is only one definition, not like this. Integral domain means this somewhere, something else somewhere else. Fields are so important that fields are just fields. Okay, so that's all the mess with zero-divisors. Next comes a nilpotent element. Now, the formal definition of a nilpotent element in a ring actually has not been given anywhere in, in that form in Herstein's topics in algebra. Instead, here and there where the notion is needed, say in talking about nilpotent linear operators. So, in the linear algebra part of Herstein, in some places nilpotence is talked about. In fact, nilpotent form is there where you encounter nilpotent matrices, there it makes an appearance. So like that. And in some exercises, it's simply mentioned. But it's not studied carefully or systematically. So this is the, you already know the definition, but still let A be a ring in our sense. We call X in A nilpotent if x to the power n is equal to 0 for some positive integer n. Okay. So that's the definition of a nilpotent element. And then the authors make a statement. A nilpotent element is a zero-divisor also, unless the ring is 0, but not conversely in general. Okay, how? We do understand that a nilpotent element is a zero-divisor, or did I get it wrong? Unless, yeah, of course. I actually was writing the correct one. For some reason, I got confused here. Okay, so let's see. Suppose that you have our ring A and X in A is nilpotent. We are saying that X will then be a zero-divisor. How? So by definition, some nth power of X is equal to 0. So by the well-ordering principle, a smallest such n also exists, for which, let me call that n0. This is equal to 0. And note also that by definition, n0 is a positive integer. So the least value it can take is 1. Now if n0 is actually equal to 1, that is one possibility, right? If n0 is equal to 1, then this equation reduces to this, so x becomes 0, and this is a zero-divisor. Because we are in a non-zero ring. Now again I got confused. Something is not correct here. If x is equal to, oh yes, I myself forgot. In the zero ring, 0 is not a zero-divisor. Okay, so this becomes a zero-divisor only because the ring is non-zero. Yes, yeah, now I got it. Okay, so that means in this case, really x is a zero-divisor. But what if n naught is greater than 1 then? Suppose n naught is actually greater than 1, then subtracting 1 from n naught will still keep the difference a positive integer. In this case, the smallest value n naught can take is 2. Even then n naught minus 1 will be equal to 1. Otherwise, it will be even larger. Alright. Now recall the minimal nature of n naught. N naught is the smallest positive integer which gives this 0 power. So if you go even smaller than that, then you will not get 0. Note also that this is also a positive integer. However, what is this? X times this. By rules of exponents, which are true in a ring for the multiplication operation, as long as your exponents are positive, this is equal to n naught, and that is equal to 0. So now what you are looking at is an equation in which you have multiplied the element x by a non-zero ring element and you have got 0. So by definition, x is a zero-divisor again. So that's how every nilpotent element is a zero-divisor. I still feel that unless how stupid, unless a is equal to 0. So a is non-zero. Okay, yeah. Now it has become clear. Yeah, I was thinking that something is still not right. Now it's okay. Oh, but not conversely in general. Any example? The element this in the ring of integers modulus 6 is a zero-divisor, but is not a nilpotent element. You can say, I am using Herstein's notation, okay, you do understand what this symbol means. This is the congruence class modulus 6 whose representative is 2. It is the set of all integers of the form 6n plus 2, where n can vary over the set of integers. Or to put it somewhat differently, it is the set of those integers which leave the remainder 2 when divided by 6. So what we are saying that this is a zero-divisor, but this is not nilpotent. Well, it's a zero-divisor because you can multiply this congruence class by this one and you will get 0, and this is a non-zero element in Z6. And it is not nilpotent because if you look at its positive powers now, you won't get the 0 congruence class. This is 4, and if you see the next power, you will get 8, but the congruence class containing 8 is just the congruence class containing 2, so you get back 2. So in this way you just keep cycling between these possibilities, 2, 4, 2, 4, like that it goes. 0 never comes. That is why it is not nilpotent despite being a zero-divisor. And then finally we have the idea of a unit. Luckily, a unit in this book is exactly the same as a unit in Herstein. We call an element x in a unit if x, y is equal to the unit element 1 or I mean the identity element 1 for some y in A. Now here we do not have any more restriction on y, that y has to be non-zero, nothing like that, just y. In fact, if your A is the 0 ring, then the x you can choose from A is 0. In that case, you can take y, I mean you can take means that is the only option. Y also 0, so 0 times 0 will be equal to 0. But in the 0 ring, 0 element is also the identity element. So in that sense, the 0 element in the 0 ring is also a unit, okay, because it follows the definition. No matter how strange that sounds, but it is true. So once you have this y, the element y is then uniquely determined by x. That is just like additive inverses are unique of elements in a ring, multiplicative inverses, if they exist, are also unique. We have already shown this before, okay, I am not going to repeat it again. This is something we should know. And we denote y by the usual notation x inverse. Minus x denotes the additive inverse of x. X inverse indicates the multiplicative inverse of x if it exists. It may not exist also. For example, in this ring, this element has no multiplicative inverse, but some other elements have. So this is not a unit, but for example, the congruence class 5 is a unit. Things like that. The units of A form an abelian group under multiplication. This is also a fact we already know from our study of ring theory in Herstein. And in fact, if you want to be sure that this is precisely the definition of units we have in Herstein, see page 145 in Herstein's book. Herstein's book means the second edition, okay. And finally, there are some other things also. Let's just complete this part. The multiples ax of an element x in A form the principal ideal We already know from Herstein what a principal ideal is. Its elements are multiples of some fixed ring element X, and the other elements by which you multiply X, of course, are coming from the ring. It is an ideal. Using the ring axioms, you can prove, in fact we already have done this in Herstein, that this is an ideal. B. Sometimes we call this ideal the ideal generated by X. We denote it by this symbol, or sometimes by AX also. Okay, because that's how the elements look in this set. So what is that relationship between, oh yes, X, okay. So X is a unit if and only if the principal ideal that X generates is equal to the entire ring A, which is also the ideal generated by the identity element. Do you see how? We already know this from Herstein, but still, do you see immediately how? Suppose that X is a unit. Okay, so that means X inverse exists. Now, X inverse or X inverse X by definition will belong to this ideal, because this is the ideal. All multiples of X, so in particular X inverse X should also be here. However, X inverse X is 1, and you know that when an ideal contains the identity element 1, it becomes the whole ring. So that is how you get this side of the implication. What about the converse? For the converse, you note that if this is equal to this, then this already is equal to this. So 1 belongs to A, and so 1 also belongs to this set. And so 1 has to be equal to something times X. That something is X inverse. And that's how X becomes a unit. So you have this side of the implication as well. And for some reason, here the authors inject this also. The zero ideal. Oh, because it's also a principal ideal generated by 0, and so it has only the 0 element, is denoted by just 0, again by abuse of notation. And finally, we have this, the ultra important notion of a field. A field is a ring A in which 1 is not equal to 0. In other words, A is a non-zero ring, and every non-zero element is a unit. That means a field is a non-zero ring in which the non-zero elements are all units. Remember that our rings are by definition commutative, and have an identity element, which Herstein calls a unit element. So being non-zero and having this property automatically means that the non-zero elements in this system form an abelian group under multiplication, and that is why it is a field. So that is the definition we have in Herstein. Conversely, if that is true, automatically this is true. So that is why field means the same thing, luckily, in that book as well as in this book. And this is where these discussions end. I mean, after that you have prime and maximal ideals, but that we will do in the next video. And tomorrow, as usual, we have calculus, and we are going to end that section, application of derivatives. I think that's what we are at right now. So we just have one or two applications in economics of the notion of derivatives, marginal revenue, marginal cost, those things we have to calculate in some situations. So that we will see tomorrow. Until then, this is me, Lucifer, from a mathematical room. Have a nice night.